So part A, let's look at the construction of our life table. A life table or mortality table is a fundamental actuarial tool used to model how a specific cohort survive and age over time. For this study, we initialize our life table with a baseline population known as the radius of 100,000 individuals, denoted as L0. Our model is built around a continuous theoretical survival function where the probability of a newborn surviving from birth to age x is given by the analytical function, where S0x is equal to 1 minus x over 100 powered by 1 over 2. This applies for each x0 until 100, tracking the survival probability across the cohort's entire theoretical lifespan. Moving on to slide 4, let's look at the specific mathematical formulas used to construct our life table component from our survival function. First, the probability of surviving, Px. This represents the probability that an individual age x survives to age x plus 1. It is calculated by taking the ratio of the survival function at age x plus 1 to the survival function at age x. Px is equal to Sx x plus 1 over by xx hx. Second, the probability of dying, Qx. This is the complementary probability, the likelihood that an individual age x dies before reaching age x plus 1. This implies Qx equal to 1 minus Px. Third, the number of survival, Lx. To find the expected number of people alive at any specific age x from our initial cohort, we multiply our starting radius L0 equal to 100,000 by the survival function at that age. Lx is equal to L0 multiply Sx at the age x. Finally, the number of deaths, Dx. This tracks the expected number of deaths between age x and x plus 1, calculated as the difference between survivors at consecutive age. Next, let's look at the remaining formula essential to completing our life table analysis. First, the percent years lived, Lx. This represents the total number of years lived by the cohort between age x and x plus 1, assuming deaths are uniformly distributed across each year of age. We calculate this by taking the average number of survivors at the start and end of the age interval. Second, the total percent years lived. This captures the cumulative number of years lived by the cohort from age x all the way until the ultimate age of the table x equal to 100. It is calculated by summing up the Ly values for all remaining age. Finally, life expectancy, Ex. This is perhaps the most prominent metric. The average number of remaining years a person surviving to age x is expected to live. We find this by dividing the total remaining person years by the number of survivors at that exact age. Moving on to slide 6, we will look at the final two actuarial metrics in our methodology, life expectancy Ex and the force of mortality Mux. First, life expectancy. As a quick recap and example calculation, this represents the average remaining lifetime expected for an individual who has reached an exact age x. For instance, evaluating this at age 1 using our calculated total person years, T1 and survival L1. Second, the force of mortality, Mux. This represents the instantaneous rate of mortality at an exact age x. It defines the limit of the probability of dying in an incredibly short time interval, conditional on survival to that exact age. Moving on to slide 7, we enter the next major piece of our analysis, risk-adjusted profile calculation. Now that we have established our core baseline life table metric, we need to factor in how specific risk profile or external interventions alter the standard mortality projection. In this section, we will explore how we adjust our baseline survival function to reflect different risk scenarios, the mathematical impact of introducing a risk factor multiplier on the cohort overall longevity, and finally, how this risk adjustment directly shifts our expected life expectancy metric. We apply our risk-adjusted framework to calculate the final modified metric, adjusted person years, and adjusted life expectancy. Once the risk factor multiplier has been applied to our survival function, it alters the distribution of survivors Lx across time. Consequently, we must recalculate our volume metric to find the true impact on longevity. First, the adjusted person years lived, LX. Using our modified survivors count, LX, we recalculate the person years lived within each specific age interval, assuming a uniform distribution of deaths within each year. Second, the adjusted total person years. Next, we aggregate this adjusted annual value to find the total remaining person years available to the cohort from age X up to the ultimate age of 100. Finally, the adjusted life expectancy. By dividing the adjusted total remaining person years by the adjusted number of survivors at that exact age, we arrive at our final risk-adjusted life expectancy. We look at the specific year-by-year impact of our risk adjustment on mortality and cohort survival, the risk-adjusted probability of death, and the adjusted survivors and death. First, the adjusted probability of dying. When a risk factor multiplier, let's call it K, is introduced, it scales our baseline probability of death. This represents the new heightened or lowered likelihood of an individual dying between age X and X plus 1. Second, the adjusted probability of surviving. Because survival and death remain complementary events, the adjusted probability of surviving to the next age is simply the complement of our new risk-adjusted mortality rate. Third, the adjusted number of survivors. To see how our cohort thins out over time under this risk profile, we calculate the remaining survivors at each consecutive age sequentially. The number of survivors at age X plus 1 is the number of survivors at age X multiplied by that year's adjusted survival probability. Finally, the adjusted number of deaths. This captures the actual volume of death occurring within that specific age interval under the new risk regime. We conclude with the macroscopic impact of our model, the rate of cohort decline, actuarial pricing implication, and the impact of compounding. First, the rate of cohort decline. By analyzing the acceleration of Tx, we see how quickly the population diminished. A higher risk factor dramatically steepens this curve yearly on, shifting the demographic profile toward an older average age much faster than the baseline model. Second, actuarial pricing implication. This structural shift directly dictates premium calculation in life insurance. Accelerated cohort decline requires higher premium reserve or increased pricing to cover the front-loaded mortality risk. Conversely, in annuities, a reduced life expectancy lowers the present value of future obligations, reducing required reserve. Finally, the impact of compounding. Mortality risks don't operate in a vacuum. The compounding effect of a constant risk multiplier K over successive years means that even a minor percentage increase in QX results in exponential reduction in survivors over time.
Before we dive into the calculation, let me explain the commutation function we use. We apply a 6% annual interest rate, which gives us a discount factor of 0.9434. The four key functions are DS, which represent discounted life, CX, which is the discounted value of death, MS, which is the cumulative present value of life insurance benefits, and NS, which is used for annuity present value calculation. This function forms the foundation for all our actuarial present value calculation. Here is a sample of our commutation tables from age 30 to 54. As you can see, the values decrease significantly with age due to the combined effect of mortality and discounting. The full table was constructed from age 30 to 100. This value were then used to calculate the actual present value for various insurance products, which we will now go through one by one. The first product we value is a life annuity of RM1,000 per year issued at age 35. The formula for the annuity due is N35 divided by D35. Substituting our commutation value, we get 0.887. Multiplying by RM1,000 gives us an actual present value of RM887.04. This means that a 35-year-old would need to pay RM887.04 today to receive RM1,000 annually for life. The relatively low value reflects the high risk profile of our policyholder. Next, we value a 10-year endowment insurance of RM50,000 issued at age 35. This policy pays the sum assured if the policyholder dies within 10 years or survives to the end of the 10-year period. The formula uses M35 minus M45 plus D45 divided by 35. The result is 0.887, which multiplied by RM50,000 gives RM44,353.80. This is quite hard because the risk-adjusted profile shows very high mortality, making the death benefit component expensive. The third product is a deferred annuity of RM600 per year starting at age 40, issued at age 35. This means the annuity payments only begin if the policyholder survives to age 40. Using our formula N40 divided by D35, we get 0.02437. Multiplying by RM600 give us only RM40.62. This incredibly low value highlights a crucial insight. The policyholder has a very low probability of surviving to age 40 due to their high risk profile. This is a powerful demonstration of how risk assessment impacts product pricing. Moving on the probability calculation, we first determine the probability that a life age 40 dies between age 40.5 and 41. Assuming a uniform distribution of death, UDD, from our life table L14 is 236 and L41 is 113. The number of deaths at age 40 is the difference, which is 123.42. The probability of dying within the year is 52.3%. Under UDD, half of this death occur in the first 6 months, so the probability of dying between 40.5 and 41 is a 0.5 times the death rate, giving us 26.14%. This indicates an extremely high mortality risk at age 40. The second calculation estimates the probability that a 43-year-old survives to age 43.55, assuming a constant force of mortality from the left table L43 23.64 and L44 10.38. The 1-year death probability is 56.1%, so the survival probability is 43.9%. And then constant force P43 0.823. The 0.55-year survival is 80.55 multiply 0.823, 63.59%. Thus, even with high annual mortality, the chance of surviving a short interval remains reasonably strong. The final product valuation is a net single premium for an RM80,000 policy that pays at the end of the year of death, but only if death occurs after age 15. The current age is 45. Using our formula with M45, M15 and D45, the ratio is 0.9023. Multiplying by RM80,000 gives us RM72,183 and 15 cents. This is extremely high because the probability of the policyholder dying after age 50 is very low. In fact, most of the risk-adjusted population has already died by age 50, so the insurance company needs to charge a high premium to compensate for the mortality risk. Now, we move to part D, where we analyze the differences between standard and risk-adjusted profiles. Our policyholder is a 30-year-old smoker who works as a construction worker and has a poor health. The total risk adjustment factor is 1.5 for smoking, 1.5 for occupation, and 1.7 for health, giving us a combined multiplier of 3.825. This means this person is nearly 4 times more likely to die compared to a standard individual. As a result, their life expectancy is extremely short and insurance for them would be very expensive. Our first comparative graph shows the probability of death by age. Both the standard and risk-adjusted lines increase with age, which is expected. However, the risk-adjusted line is dramatically higher at every age. By age 18, the risk-adjusted probability of death reached nearly 100%, while the standard probability is only 27%. The widening gap shows that as the policyholder age, they are already high risk because even more severe. This has a significant implication for insurance pricing and risk management. The second graph shows the number of survivors by age. For the standard population, we see the typical survival curve when many individuals live to old age. However, for the risk-adjusted population, the number of survivors drops sharply at a very young age. By age 16, almost all of the high-risk group has already passed away. This means that traditional retirement planning and long-term insurance products are almost irrelevant for this individual. The high mortality at young age completely changes the financial landscape. The third graph illustrated life expectancy by age. A standard 13-year-old can expect to live more than 19 more years. By a high-risk 13 years old with our profile is expected to live less than 1 more years. That's a drop of over 99%. This stark difference shows how small risk multipliers, when applied year after year, create a massive compounding effect. The risk-adjusted person's life expectancy drops by decades, and this completely changes their financial future. Traditional retirement planning becomes irrelevant for such individuals. Now, let me share our reflection. The most challenging aspects of this project was calculating life expectancy for the risk-adjusted table, because the risk-adjusted group has very high death rates at young age. The number of survivors becomes zero very quietly. When we use the standard mathematical formulas, we got negative value or extremely large number for all the age. This happened because the formula assumes people live to old age, but in the risk-adjusted table, nobody survives that long. Fixing the formula to work correctly for a truncated table was technically challenging and required us to think carefully about the assumption embedded in the formulas. The biggest lesson was how a small risk can grow into a huge cost. We started with one idea. A high-risk person has 3 times higher chance of dying each year. But when we were repeated this year after year, the effect became massive. That person's lifespan dropped by many years. Their insurance costs become many times higher. This shows us that daily choices and dangerous jobs are not small things. They can change a person's whole money future. Normal retirement plans no longer work for them. Now we see why actuarial study rates so carefully in real life. Thank you for listening.